Welcome! In this session, we'll tackle LeetCode problem number 1509, minimum difference between largest and smallest value in 3 moves. This problem requires us to find the minimum difference between the largest and smallest elements of an array after performing up to 3 removals. Let's dive in. In this problem, we are given an integer array called nums, and our goal is to determine the minimum possible difference between the largest and smallest values of the array after removing exactly 3 elements. Essentially, by removing 3 elements, we want to minimize the range of the remaining numbers. If the array has 3 or fewer elements, the solution is straightforward. We can remove all the elements, leaving no numbers behind, which means the difference would simply be 0. Now, the input is structured as a list of integers, where the array can contain anywhere from 1 to 100,000 elements. The values in the array can range from -1 billion to +1 billion. The output should be a single integer representing this minimum difference after performing the 3 removals. Let's explore this concept with an example. Suppose we have the array nums equals 5, 3, 2, 4. First, we sort this array to get 2, 3, 4, 5. Now, after removing 3 elements, we are left with one number in the array. For instance, if we remove 2, 3, 4, the only remaining number is 5. In this case, the smallest and largest values are both 5, so the difference is 5 equals 0. This illustrates a scenario where removing 3 numbers results in no range at all, and the minimum difference is therefore 0. Now, let's consider another example with a slightly larger array, nums equals 1, 5, 0, 10, 14. When we sort this array, we get 0, 1, 5, 10, 14. After removing 3 elements, we calculate the differences between the smallest and largest remaining numbers for all valid removal combinations. For instance, if we remove 14, 10, 5, the smallest and largest remaining values are 0 and 1, giving us a difference of 1. If we remove 0, 1, 5, the smallest and largest values left are 10 and 14, resulting in a difference of 4. Testing other combinations, such as removing 0, 5, 14, leads to even larger differences. Ultimately, the smallest possible difference is 1. Let's look at another example to deepen our understanding. Here, we have nums equals 6, 6, 0, 1, 1, 4, 6. After sorting, the array becomes 0, 1, 1, 4, 6, 6, 6. Now, we examine the possible outcomes of removing 3 elements. If we remove all the largest values, 6, 6, 6, the smallest and largest remaining numbers are 0 and 4, giving us a difference of 4. On the other hand, if we remove the smallest values, 0, 1, 1, the smallest and largest remaining numbers become 4 and 6, resulting in a difference of 2. Since 2 is smaller than 4, the minimum difference for this example is 2. Let's now consider the constraints and edge cases for this problem. The array can contain up to 100,000 elements, which means we need an efficient solution since brute force approaches would be too slow. Each element in the array can be as small as -1 billion or as large as +1 billion, so the algorithm must handle extreme values gracefully. If there are 3 or fewer elements in the array, the problem simplifies because we can remove all of them, resulting in a difference of 0. For edge cases, if the array has just 1 or 2 elements, the output will always be 0. If all elements in the array are identical, such as 7, 7, 7, 7, the difference is also 0 because there's no range to minimize. Finally, for large arrays with mixed negative and positive values, the algorithm must ensure that the removals are strategically chosen to minimize the difference efficiently. To solve this problem, we must ensure that the solution is both efficient and robust enough to handle large inputs, extreme values, and various edge cases. The algorithm should effectively balance computational speed with accuracy, especially when dealing with arrays containing up to 100,000 elements. Additionally, the solution must account for scenarios like small arrays, arrays with all identical elements, and arrays with a mix of negative and positive numbers. By addressing these considerations, we can confidently compute the minimum difference in the range of values after 3 removals. To tackle this problem, we first considered a brute force approach. The idea here is to explore all possible combinations of removing 3 elements from the array. For each combination, we compute the difference between the largest and smallest values in the remaining elements, and ultimately return the smallest difference found. However, this approach has a major inefficiency. Since the number of combinations grows exponentially as the array size increases, the time complexity becomes n cubed. This means it's computationally impractical for larger arrays and doesn't make use of any inherent structure in the problem to optimize the solution. This led us to think more strategically about how to narrow down the possibilities and avoid such exhaustive computations. That's where the optimized approach comes in, based on a few key observations about the problem. The optimized approach relies on sorting the array and strategically evaluating only a few scenarios. First, we note that after removing 3 elements, we're left with n-3 elements, and our goal is to minimize the difference between the largest and smallest remaining elements. To achieve this, we should focus on either removing the largest 3 elements to reduce the upper bound or removing the smallest 3 elements to increase the lower bound. Sorting the array is key because it allows us to directly access the smallest and largest elements efficiently. This gives rise to 4 specific cases to evaluate: removing the 3 smallest elements, removing 2 smallest and 1 largest, removing 1 smallest and 2 largest, or removing the 3 largest elements. By calculating the difference for each of these 4 cases, we can identify the minimum difference without having to generate all possible combinations. This significantly reduces the computational effort while still ensuring that we explore all meaningful possibilities. When comparing the brute force approach to the optimized one, the trade-offs become clear. While brute force is easier to conceptualize, its n cubed time complexity makes it completely impractical for large inputs. The optimized approach, on the other hand, is slightly more complex in terms of logic but achieves a time complexity of n log n, thanks to sorting the array, which makes it much more efficient for larger datasets. Both approaches use additional space aside from the input array, so there's no difference in space complexity. Ultimately, the optimized approach is the best choice because it balances efficiency, simplicity, and correctness, ensuring we solve the problem both accurately and practically. To tackle the problem of minimizing the difference between the largest and smallest values in an array after removing exactly 3 elements, we start by understanding the input and output. The input is an array of integers, and our goal is to compute the smallest possible difference after eliminating any 3 elements. One way to approach this is by generating all possible combinations of 3 elements that can be removed. For instance, if the array is 1, 5, 3, 7, we can consider removing combinations like 1, 5, 3, 1, 5, 7, and so on. For each combination, the remaining array will have a specific maximum and minimum value, and our task is to calculate the difference for each scenario. By systematically iterating through all these combinations, we can ensure we find the smallest difference. The formula for generating combinations, Cn3, gives us the total number of ways to choose 3 elements from an array of size n. Now that we understand the setup, the next step involves iterating through each combination of 3 elements to remove. For every combination, we extract the remaining subarray by using a temporary copy of the input array. This ensures the original array remains unchanged. Once we have the subarray, we calculate the difference between its largest and smallest values. This involves finding the maximum and minimum values of the subarray and subtracting the minimum from the maximum. To keep track of the smallest difference encountered, we use a variable called min_difference, initialized to infinity. Each time we compute a difference, we compare it with min_difference and update it if the new value is smaller. After looping through all combinations, the value of min_difference will hold the result, which is the smallest possible difference for the given array. The brute force approach is a great starting point because it ensures correctness by exhaustively evaluating all possible ways to remove 3 elements. However, this method is computationally expensive, especially for larger arrays, because generating all combinations has a time complexity of n cubed. This makes it impractical for arrays with thousands of elements. Despite its inefficiency, brute force provides an intuitive understanding of the problem. To optimize, we later explore methods like sorting that significantly reduce the complexity. Regarding data structures, we rely on a temporary array to represent the subarray after removing 3 elements. This prevents us from altering the original input data during the process. Additionally, the variable min_difference helps efficiently track the smallest difference encountered across all iterations. The key operations in this approach involve generating combinations, finding the maximum and minimum values, and updating the smallest difference. Generating combinations of 3 elements from an array of size n is the most time-consuming step, with a complexity of n cubed. Once we have a combination, calculating the maximum and minimum values of the remaining subarray takes n. Finally, comparing and updating the min_difference variable is a constant time operation, O(1). For example, if the array size is 5, we would generate combinations like A, B, C, and A, B, D, and for each combination, we perform these key operations. Together, these steps define the overall computational cost of the brute force solution. When considering edge cases, it's crucial to handle scenarios that could break the algorithm. For instance, if the array size is exactly 3, removing all elements results in an empty array. Here, we can return 0, as the difference is undefined. Arrays with duplicate values, such as 1, 1, 1, 1, simplify the problem because the difference will always be 0, regardless of which elements are removed. Negative values also require careful handling since both the minimum and maximum could be less than 0, affecting the difference calculation. Finally, when analyzing complexity, the brute force approach has a time complexity of n cubed *n, which simplifies to n to the power of 4, and a space complexity of n, due to the temporary array used for subarrays. These limitations highlight the need for optimized methods for larger input sizes. This solution efficiently solves the problem of minimizing the difference between the largest and smallest values in an array after removing exactly 3 elements. The function starts by checking if the array contains 4 or fewer elements. In such cases, removing 3 elements leaves at most 1 element, so the difference is 0. Next, the array is sorted, which prepares it for a systematic evaluation of scenarios where 3 elements are removed. Sorting ensures that the smallest and largest elements are easily accessible. The main idea is to consider 4 possible ways of removing 3 elements. 1. Removing the smallest 3 elements, which leaves the largest remaining elements. 2. Removing the smallest 2 elements and the largest 1 element. 3. Removing the smallest 1 element and the largest 2 elements. 4. Removing the largest 3 elements, which leaves the smallest remaining elements. In each case, the code calculates the difference between the new maximum and minimum values in the array. Finally, the minimum of these 4 differences is returned as the result. This approach ensures that all possibilities are considered, and the solution is efficient with a time complexity dominated by the sorting step, which is n log n. The solution is well suited for the problem constraints and provides the correct result for all input cases efficiently. This is the Java implementation of LeetCode problem number 1509. The logic mirrors the Python solution and involves sorting the array to simplify the process of determining the minimum difference when removing 3 elements. The main difference in Java is the use of explicit type declarations, the arrays.sort method for sorting, and math.min for computing the minimum across the 4 scenarios. The implementation ensures clarity and efficiency while adhering to Java conventions. In this problem, we are tasked with minimizing the difference between the largest and smallest values in an array after performing at most 3 removal operations. To understand how to approach this, let's look at the first example where the input array is given as nums equals 6, 6, 0, 1, 1, 4, 6. The length of the array is 7, which is greater than 4, so we proceed by sorting the array. After sorting, the array becomes nums equals 0, 1, 1, 4, 6, 6, 6. Sorting helps us to easily evaluate different scenarios for removing elements and calculating the minimum difference. Now, we evaluate the possible scenarios for removing exactly 3 elements to minimize the difference between the largest and smallest values. The first scenario is removing the 3 smallest elements, leaving the range between the largest value and the 4th smallest value, nums-1, nums3, equals 6, 4 equals 2. The second scenario is removing the 2 smallest elements and the largest one, resulting in nums-2, nums2, equals 6, 1 equals 5. The third scenario involves removing the smallest element and the 2 largest ones, producing nums-3, nums1 equals 6, 1 equals 5. Finally, the fourth scenario is removing the 3 largest elements, leaving the range between the smallest value and the 4th largest value, nums-4, nums0 equals 4, 0 equals 4. Among these, the smallest difference is min, 2, 5, 5, 4 equals 2. Therefore, the output for this example is 2. In the second example, the input array is nums equals 1, 5, 0, 10, 14. The length of the array is 5, which is greater than 4, so we sort the array. After sorting, the array becomes nums equals 0, 1, 5, 10, 14. Next, we evaluate the 4 scenarios for removing 3 elements. Removing the 3 smallest values leaves the range between the largest value and the 4th smallest value, nums-1, nums3, equals 14, 10 equals 4. Removing the 2 smallest values and the largest one gives nums-2, nums2, equals 10, 5 equals 5. Removing the smallest value and the 2 largest ones results in nums-3, nums1, equals 5, 1 equals 4. Finally, removing the 3 largest values leaves the range between the smallest value and the 4th largest value, nums-4, nums0, equals 1, 0 equals 1. From the calculations, the smallest difference in example 2 is min, 4, 5, 4, 1 equals 1. Therefore, the output for this example is 1. Now, let's consider the third example where the input array is nums equals 100, 100, 100. The length of this array is 3, which is less than or equal to 4. In this case, we can remove all but one element, so the difference between the largest and smallest values becomes 0. Hence, the output for this example is 0. To analyze the time complexity of this solution, we start by breaking it into its individual steps. First, we calculate the length of the input list, n, using the built-in len, nums, function, which is an O1 operation. Next, we check whether n is less than or equal to 4 with the condition if n equals 4. This is a simple comparison and also takes O1 time. Now, the most significant part of the solution is the sorting step, where we use Python's built-in sort method. This method is implemented using timsort, which has a time complexity of n*log n, where n represents the size of the array. Finally, after sorting, we calculate the minimum difference by evaluating 4 fixed scenarios. This involves accessing specific indices of the sorted array and performing basic arithmetic operations. Since accessing an element by index is O1, and we only evaluate 4 scenarios, this step takes O1 time overall. Therefore, each of these individual steps contributes differently to the total time complexity. When we consider the total time complexity, sorting the array dominates all other operations. Sorting takes n*log n, while calculating the length, checking the condition, and evaluating the result all take constant time, O1. As a result, the overall time complexity of the solution is n*log n. Moving on to the space complexity, we analyze the memory usage. The input array, nums, is stored in memory, and since the sorting is done in place, no additional space is used to create a copy of the array. Apart from the input, the solution uses a few temporary variables to store intermediate values, but these variables require only constant space, O1. Therefore, the total space complexity is O1, as no extra data structures or memory-intensive operations are involved beyond the in-place sorting and constant temporary storage. To put this into perspective, we can compare the optimized solution with a naive approach. A brute force method would involve generating all possible combinations of removing 3 elements from the array. This requires computing combinations, which takes n³ operations in the worst case. For each combination, we would then calculate the maximum and minimum of the remaining elements, which takes n. This results in an overall time complexity of n to the power of 4, which becomes computationally prohibitive for larger arrays. In contrast, the optimized solution simplifies the problem by leveraging sorting and restricting the evaluation to 4 fixed scenarios, reducing the complexity to n*log n. This makes the solution highly efficient and scalable for larger input sizes. Furthermore, the time complexity remains consistent across best, average, and worst cases, as the sorting operation always takes n*log n. The space complexity also remains O1, regardless of the input size. To mathematically verify the big O, sorting dominates at n*log n, while constant time operations like indexing and subtraction contribute O1. Adding these together, the overall complexity is conclusively n*log n. When tackling problems like this, there are a few common mistakes to watch out for. First, not sorting the array when necessary can lead to incorrect results. Sorting is essential for simplifying the process of finding the k smallest or largest values, which is often the key to an efficient solution. Another frequent mistake is overcomplicating the problem. For variations that only require removing a few elements, many people attempt exhaustive searches or combinations, which can be avoided by focusing on edge cases like the smallest or largest elements rather than exploring every possibility. Additionally, ignoring edge cases can trip you up. For example, consider arrays with fewer than 3 elements, arrays where all values are the same, or those containing both very large negative and positive numbers. Failing to account for these scenarios can lead to runtime errors or incorrect outputs. Lastly, when implementing optimized approaches, errors in the use of sliding window or two-pointer techniques are common, such as misplacing pointers or mishandling window sizes. These often result in off-by-one errors or skipped elements, so careful implementation is key. Another common pitfall is misunderstanding constraints. For example, if the array size can go up to 100,000, choosing an inefficient solution like O in superscript 3 will likely exceed time limits. It's crucial to design solutions that align with the problem's constraints. Now, when it comes to interview scenarios, there are a few key insights to keep in mind. Pattern recognition is a valuable skill. Many problems involving removing k elements to optimize a result revolve around sorting and analyzing boundary cases. Focusing on the smallest and largest elements of the array can lead to a more efficient approach. Additionally, consider trade-offs in your solution. While brute force methods can guarantee correctness, they are impractical for large inputs. Optimized techniques, such as sorting, can reduce complexity to O n log n and eliminate unnecessary computations. During interviews, clear communication is essential. When discussing edge cases or trade-offs, explain your assumptions explicitly and justify your choices. Finally, test edge cases early in your implementation process. For instance, testing small arrays or those with all identical elements can help you catch flaws and ensure your solution is robust. To deepen your understanding, it's helpful to recognize related problems that share similar patterns or techniques. For instance, LeetCode 1465, which involves finding the maximum area of a piece of cake after making cuts, or LeetCode 1353, which focuses on maximizing the number of events that can be attended, both require strategic decision-making similar to this problem. Other examples include LeetCode 217, about identifying duplicates, and LeetCode 1423, which deals with maximizing points from cards. Exploring these can broaden your problem-solving toolkit. Now, let's discuss alternative approaches and their trade-offs. The brute force method, which generates all possible combinations, has a complexity of O in superscript 3. While this guarantees correctness, it's practical only for small input sizes, such as n less than or equal to 20. On the other hand, a sorting-based approach combined with a window technique offers a more efficient alternative. Sorting the array has a complexity of O n log n, and traversing a window adds only O k, making it optimal for larger inputs. These trade-offs highlight the importance of selecting the right approach based on the problem's constraints. Another efficient strategy is the sliding window technique. With a complexity of O n, it is particularly effective for fixed-length subarray problems. However, it requires careful pointer management to avoid common pitfalls, such as misaligning the window or skipping elements. This approach is ideal when the problem involves continuous subarrays and benefits from its linear runtime, making it a great tool for handling larger datasets efficiently. By mastering these techniques and understanding when to apply them, you'll be well prepared to tackle variations of this problem and similar challenges. To wrap up, we reviewed the problem, discussed the brute force approach, and highlighted key takeaways. Remember, problems like this help sharpen your skills in constrained optimization and array handling. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!